Ladies and gentlemen, welcome back to lesson 22 in group theory. This lesson will talk about the fundamental theorem of homomorphisms, a very important theorem that answers a pretty simple question. If you take a look at the diagram here, we see that we have three groups, G, K, and H. We see that we have a homomorphism from G to H, call it phi, and another homomorphism from G to K, call it psi. And we also include the condition that psi has to be surjective. That means that any element in K is the image of some element in G by psi. The question now, does there exist a homomorphism going from K to H such that this homomorphism makes the diagram a commutative diagram? A commutative diagram is a diagram in which the direction you traverse does not matter. You will end up in the same result. So if we go from the direction of phi, or if you go from the direction that covers psi and this homomorphism, then the result would be the same. So if that homomorphism exists, is it a unique homomorphism? That means if there was another homomorphism with the same property, would it be equal to our original homomorphism? Let's get to it. Throughout this statement and the proof of this theorem, I'm going to keep this diagram somewhere on the screen so that you can always refer to it when needed. So for the official statement of the theorem, we have that G, H, and K are three groups. We have that phi going from G to H is a homomorphism, and that psi going from G to K is an epimorphism, so a surjective homomorphism. We have four results. The first result is that there exists a homomorphism rho going from K to H such that rho is done in a way that rho composed with psi is equal to phi, and this is if and only if the kernel of psi is a subgroup of the kernel of phi. If rho does exist, then the three next results apply. The second one says that it is unique. The third one says that the image of rho is equal to the image of phi. In particular, rho is a surjective homomorphism if and only if phi is a surjective homomorphism. And number four says that if we take the two sets, psi of kernel of phi and kernel of rho, we find that they're equal. So in particular, rho is injective if and only if the kernel of psi is exactly equal to the kernel of phi. So notice here that to have an existence, we need to have the inclusion of the kernel of psi inside kernel of phi. But furthermore, if we have that rho is injective, then this inclusion becomes an equality. So let's get down to the proof. Okay, here's the game plan in proving the first part of the theorem. We will prove this if and only if by doing the forward direction first. So in the forward direction, we will suppose that there exists rho, a homomorphism going from K to H, such that phi is equal to rho composed with psi. So if rho exists, we want to prove that care of psi is a subgroup of care of phi. But the good news is, we already know from previous lessons that care of psi is a subgroup of G. And so it suffices to prove that care of psi is a subset of care of phi, not a subgroup. Because since this is a subgroup of G, that means it's a group in its own right. So if it's a subset of care of phi and it is a group, that means it's a subgroup of care of phi. That means that any element in care of psi will definitely be found in care of phi. So we let any element G in care of phi, let G be an element in care of psi. We need to prove that G is inside care of phi. So we have, since G is in care of psi, that means that if we take phi of G by definition of rho, remember, phi is equal to rho after psi. So phi, we can replace it by rho after psi. But because G is in the kernel of psi, then psi of G is equal to the identity, rho of the identity. And we know that a homomorphism carries the identity to the identity. And since rho is a homomorphism, this is equal to the identity. So this means that phi of G is equal to the identity, proving that G is an element in the kernel of phi. So G is in ker phi, thus proving the inclusion of ker psi inside ker of phi. And since ker psi is a group, we can automatically say that ker psi is a subgroup of ker of phi, thus completing the forward direction of the if and only if statement. Now for the backwards direction. The backwards direction is supposing this is true and then constructing a homomorphism, proving that there exists a homomorphism by constructing it. So we suppose that ker of psi is a subgroup of ker of phi. That means it's inside ker of phi. Let K be an element in K. Since psi is an epimorphism, meaning that it is surjective, there exists an element G such that psi of G is equal to K. And this is true for any K in K because psi is surjective. We want to see a commutative diagram. We want to see that rho of K, which is equal to rho of psi of G, I just replaced K by psi of G, to be equal to phi of G, thus ensuring a commutative diagram. In other words, a diagram that does not take into account the direction you use, you're always going to end up in the same result. So to ensure that, we define our homomorphism rho of K by simply the most natural choice, which is phi of the pre-image of K by psi, which is G. So basically, for any K in K, we take rho of K by taking the G first, which is the pre-image of K by psi, and then we apply phi to it. And that's how rho is defined. So the first thing to prove here is that rho is a well-defined map. The reason it's well-defined is that if G1 and G2 are elements in G such that psi of G1 is equal to psi of G2, since remember the input that we put is going to be equal to K, which is the psi of some G in G. So we start with this. Then we have that the identity is equal to psi of G1, psi of G2 inverse. So all what I did is I used this equation here by multiplying both sides by psi G2 inverse. And because psi is a homomorphism, this is psi G1, G2 inverse. That means G1, G2 inverse is in the kernel of psi. Now, what did we suppose in this if statement? The backward direction. We have supposed that the kernel of psi is included in the kernel of phi. So any element in the kernel of psi is an element in the kernel of phi. And since this is an element in kernel of psi, which is included in kernel of phi, that means that G1, G2 inverse is an element in the kernel of phi. And so because it's in the kernel of phi, by definition of kernel, if we apply phi on G1, G2 inverse, we get the identity element. And I can just write it in the opposite direction. 1 is equal to phi of G1, G2 inverse. And because phi is a homomorphism, we can split it up into phi of G1, phi of G2 inverse. And now I multiply both sides by phi of G2, giving me phi of G1 is equal to phi of G2. But remember, the definition of rho was giving the phi of the G. So because I have two equal elements in the domain, I have two equal elements in the image of rho, telling me that rho is well defined, finishing the proof of rho being a well-defined map. Let us prove now that rho is a homomorphism. This proof is direct. We use two elements k1 and k2 in K, the domain of rho, and we know that since psi is surjective, then every k in K is going to be the image of some G. So I'm going to say it's G1 and G2 in G, such that psi of G1 is equal to K1 and psi of G2 is equal to K2. Then we have that rho of K1, K2. By definition of rho, this is equal to phi of G1, G2. But because phi is a homomorphism, we can split this up into phi of G1, phi of G2. And this is exactly, by definition, rho of K1 and rho of K2. Successfully proving that rho is a homomorphism and completing the backwards part of the if and only if statement. The second part says that if rho, the homomorphism, exists, then it has to be unique. That means if there is another map with the same functionality as rho, call it rho tilde, then rho is equal to rho tilde. Suppose rho exists and there exists a rho tilde going from K to H, another homomorphism, such that the same way as rho tilde composed with psi is equal to phi. You know already that we know that rho composed with psi is equal to phi. So this means that we have now two homomorphisms that have the same functionality. We prove that they're equal. They're equal, it means that if they take one input, they give the same output. So if we have an input k in K, we know since psi is surjective, then K is the image of some G in G. So psi of G is equal to K. Then rho tilde of K, we'll just replace K by psi of G. And now we have that rho tilde psi is equal to phi of G. But phi of G is also equal to rho psi of G. And rho psi of G is equal to rho of K. Because I know that psi of G is equal to K. So I've just successfully said that rho tilde K is equal to rho K. So it gives the same image for any K in K. Therefore, rho tilde is equal to rho and rho is unique, proving the second part of the theorem. In the third part, I'd like to prove that the image of rho is equal to the image of phi. This is an equality of sets. I'm going to prove it by double inclusion. Let an element be an image of phi. An element in image of phi would have the form phi of G for some G in G because it's in the image. So it has to be the image of some element in G. So because of the definition of rho with psi equaling phi, we get that phi of G is equal to rho of psi of G. But rho of psi of G is an element in the image of rho. Because it is the image of some element by rho. So this means that an element in the image of phi is an element in the image of rho. So image of phi is a subset of the image of rho. Proving the forward inclusion. For the backwards inclusion, if We have an element in the image of rho, which looks like rho of k for some k in k. Because psi is surjective, we have that there exists a g in g, such that psi of g is equal to k. This is because psi is surjective. So if we have a look at rho of k, that's going to be rho of some psi of g, as per the definition here. And this is equal to phi of g. And phi of g is in the image of phi, because this is an image. And so we have just proven that rho of k, which is in the image of rho, is also in the image of phi, giving us that image of rho is included in the image of phi, giving us the backward inclusion as well, completing the equality. Image of phi is equal to image of rho. So now, because we have that the image of phi is equal to the image of rho, if we have the if and only if statement, rho is a surjective homomorphism. If and only if the image of rho is equal to the entire codomain of rho, but the entire codomain of rho is equal to H. And that is equal to the image of phi, but H is the codomain of phi as well. So this is if and only if phi is surjective. Completing the proof of the third part of the theorem. The fourth and last part will be the equality of the sets psi of ker phi and ker rho. This will be also done by double inclusion. We will do the forward inclusion now. This will also be done by double inclusion. Let us start with the backwards inclusion, starting with an element here, proving that it is an element here. So let k be an element in the kernel of rho. This means that rho of k is equal to the identity. There exists a g in g such that psi of g is equal to k, because, again, psi is surjective. Now, we know that this is true, so we're going to start with the identity, saying that this is equal to rho of k. But what is k? K is psi of g. And rho of psi of g is equal to phi of g. So this means that phi of g is equal to 1. G is an element in the kernel of phi. So if g is an element in the kernel of phi, and you apply psi on both sides, then this means that k, which is equal to psi of g, is an element in psi of ker of phi. We just proved that if k is in ker of rho, then k is an element of psi of ker of phi, finishing the backward inclusion. Ker rho is included in psi of ker of phi. Let us do the forward inclusion now, supposing there is an element here and proving the element lies in here. So let G. So we will not suppose there is an element exactly here. We will start with an element that is in here. So G is in the kernel of phi. So if G is in the kernel of phi, then phi of G is equal to 1. We have that psi of G is an element in psi of ker of phi, because all what you did is apply psi on both sides, and the identity is equal to phi of G, but phi is equal to rho of psi of G. So this means that psi of G is an element of ker rho, because rho of this element gives the identity. So this means this element has to be in the kernel of rho. So we've just proven that an element in psi of ker of phi is going to be included in ker of rho, proving the forward inclusion. Thus proving the equality, psi of ker of phi is equal to ker of rho. Now we know by a previous result of injectivity of homomorphisms that rho is injective if and only if the kernel of rho is trivial, containing only the identity element. But we've seen just now that the kernel of rho is equal to psi of the kernel of phi. So this means that this is also equal to the identity. So this means that psi sends all of these guys to the identity. That means all of these guys have to be some elements in the kernel of psi. So the kernel of phi has to be inside the kernel of psi. Because recall that the kernel of psi is what? It's all of the elements that send to the identity of psi. But we know that psi of these elements send to the identity, so these elements have to be inside the kernel of psi. Thus we have proven this inclusion. We have already the other inclusion. We can say that kernel of phi is equal to kernel of psi, completing the proof of the fourth and the final part of this theorem, the fundamental theorem of homomorphisms. Okay, let us now take a simple example. G is Z, H is ZMZ, and K is ZNZ. And our phi goes from G to H is defined to be taking the integer x and giving us x modulo m. We can take it as the notation x between two brackets modulo m. For example, if m was 2 and we had x is equal to 12, then 12 would give us 0 modulo 2 because 12 is an even number. So it gives a remainder of 0 when divided by 2. Now we do the same with psi, giving us the integer x modulo n with a similar notation. Using now the fundamental theorem of homomorphisms, we know that since phi is a homomorphism and psi is an epimorphism, we have that there exists a rho between z and z to zmz, defining to be taking the integer x mod n, giving us x mod m. And this is exactly the definition of phi of x. There exists such a phi if and only if, remember the first result, the kernel of psi is inside or a subgroup of the kernel of phi. It just suffices to say a subset for now. We don't really care about subgroups. Let's just consider it being a subset because that's sufficient. So the kernel of psi, taking the integer mod n, is included in the kernel of phi, taking the integer mod m. What is the kernel of psi? Kernel of psi is all of the integers that give 0 modulo n. What are the integers that give 0 modulo n? Well, these are the integers that when you divide by n, you get a remainder of 0. So essentially saying this is nz, all the multiples of n. And the same here. What are the integers that when you divide by m, you get 0 as a remainder? Now that's the multiples of m. So this is multiples of n, and this is multiples of m. So when is the set of the multiples of n included in the set of the multiples of n? Well, this is true if and only if m divides n, or another way to say it, n is divisible by m. And how is that possible? Well, if you take an example, n is equal to 6, m is equal to 2, we know that since 2 divides 6, we have that the multiples of 6, which are, let's say, 0, minus 6, 6, 12, minus 12, etc. All of these are even numbers, so they're inside the multiples of 2. The set of the multiples of 2, 0, 2 minus 2, 4 minus 4, all of the multiples of 2. So because we have that the kernel of psi is included in the kernel of phi, and there exists this homomorphism giving us from an integer modulo 6. So the row here takes an integer modulo 6, giving us the integer modulo 2. For example, row of 0 modulo 6 is equal to 0 modulo 2. Row of 3 modulo 6 is equal to 3 modulo 2. But 3 modulo 2 is equal to 1 modulo 2, because 3 is an odd number. If you divide it by 2, you get a remainder of 1. So that's equal to that. Row of 5, for example, is also going to be at the end 1 modulo 2. And moreover, this row is unique, as we have proven. In other words, there is no other row that we can define based on the definitions of phi and of psi. Of course, if we change the definitions of psi and or psi, then the row will change accordingly. The row is specifically designed to make this diagram a commutative diagram. That means that whether you go in this direction, taking an integer straight to zmz, or you go the long way, taking an integer, make it modulo n and then modulo m, the row will make sure that your trip is going to be the same either way. This has been the lesson. If you've enjoyed, drop a like, subscribe, share with anyone who'd be interested in this nice topic. I'll be dropping more content on group theory. Have a nice day and bye.